Okay, we're recording. So, here's what we were talking about last time. I was trying to make sense out of this business where we have a normal vector that shows up in our formula for circulation density, right? So here was the big formula for circulation density, and there's this question of why is that there? You'd think it would be intrinsic to the vector field. So I pointed out last time that, well, actually no, we've seen previously where a density, namely change density, when we were looking at the fundamental theorem of line integrals, has that same sort of mysterious sort of, well, there's an orientation vector in there. So this is not really a new thing. So let's think, though, what does that mean, and how does this change our interpretations? Well, the interpretation that I pushed when we were talking about change density is that when you regroup that orientation vector into the vector differential as it should be, right? I mean, as is really more natural. Then the idea is, don't think of a density as something you multiply by a size to get a quantity. Think of this now as an oriented density that you multiply by an oriented size, if you will, right, to get the quantity. Anyway, we're going to do the same thing we did last time already. Let me do it again. Same point of view here, looking at Stokes' theorem. Again, we have this kind of unexpected, at least at a glance, first glance, seemingly unexpected appearance of an orientation vector. And I'm going to group that together with ds scalar to make the vector ds vector differential, again, as it should be. That's what is describing the little piece of the surface. That is how it really should be, right? And having done that, rather than thinking of a density as something you multiply by size to get a quantity, let's reinterpret an oriented density as being something you multiply by an oriented size. Keep in mind, that's what the ds vector is. An oriented size, manner of speaking, to get, again, the quantity in question. Okay, so, like I say, we've actually been down this road before. It's, now, geometrically it's very different. It's surfaces instead of curves. It's normal orientations instead of tangent orientations. So, appropriately different, appropriate to the context, of course. But, that said, very analogous, right? So not really that different of a situation. And in the same way that you can, if I claim that we're going to think of gradient as oriented density, and we can interpret geometrically from that. The magnitude is telling us, generically, independent of the actual curve, generically how fast is the function changing, in its maximal direction. And it is also telling us what that maximal direction is, right? Likewise, there are interpretations you can make of the oriented circulation density, namely curl. And that is that, again, there's a magnitude and a direction. The magnitude is telling you how much is this fluid really rotating. Just, scalar quantity, just, in terms of magnitude, how powerful of a twister is this, right? And then by way of the direction vector of the curl, that's telling you around what axis is that twister rotating, right? So here's a picture of that. I'm trying to make a little sense out of this following. But let's suppose you have a vector field like so, right? Let's see. It's kind of rotating kind of around like this. It's not a purely vertical rotation around a horizontal axis, and it's not a purely horizontal rotation about a vertical axis. It's kind of at an angle or something, right? So the curl vector is going to tell you two things. It's going to tell you how much of a rotation is there? How violent of a twister is this, right? Is it a fast rotation around an axis, or is it a kind of a gentle, slow sort of a thing? And then it's going to tell you what the axis is that rotation is rotating around. And this is this is one of the differences. It's just the way geometry works. One of the big differences between rotations in space versus rotations in the plane. If you're talking about rotations in the plane, well, there's clockwise and counterclockwise. That's pretty much the end of the story on which direction the rotation is. And in space, it's much more complicated. In space, you could be rotating around this axis, or you could be rotating around that axis, or you could be rotating around a vertical axis. There's much more sort of like flexibility, different ways in which the rotation can happen. Okay. All right, so let me try to now draw some more pictures to hopefully illustrate how dot product with the normal vector actually does exactly what it ought to. It does exactly what we need. So imagine, again, hypothetical, we have a vector field representing a flow of a fluid. My favorite metaphor anyway for this context. So there's our vector field, flow of a fluid, and of course we've got a curl here, right? And now let's suppose that I'm looking at a surface, little piece of surface here, and I'm interested in the how much circulation we have around that boundary of that little piece of surface. So with this this context having been set, let's draw first a picture of what does it look like. I mean, when I say that this vector field, that this fluid is truly significantly flowing along that boundary, right? There's the flow of the fluid. Here's the boundary. You can see that they are in the same direction. The flow is like this, right? Follow the tip of my finger there. The boundary is like this, and that fluid really is flowing along that boundary. So what's the normal vector got to do with this? This is the algebraic way that we detect that this fluid going around in circles, of a sort, is flowing along this boundary curve as we have it drawn. And so here's again the curl vector. Here's the normal vector. And notice that the geometry of the flow and the boundary going in the same direction is really the same geometrically. It's just coincidental with the curl and the normal vector going in the same direction, right? Just geometrically, the boundary and the circulation of the fluid lines up coincidentally with those two vectors lining up. Does that make sense? Everybody see kind of how those are just, they're unavoidably connected to each other. And then, by contrast, of course, another perfectly reasonable possibility, let's suppose that, again, we have a fluid flowing kind of around like this. Same fluid, same exact fluid, but now let's suppose that my surface is just oriented a different way. And so, naturally, its boundary is oriented a different way. Right, so now we've got a very different scenario. The fluid's doing this. The boundary, I don't know if I have the coordination to... Okay, this is harder than it looks. The fluid's doing like that. The boundary is doing like this. I can't do them at the same time. But there's a mismatch, right? If you look at what the fluid is doing, let me go back to blue here. The way that the fluid is kind of rotating around, it's just totally different from the way that the boundary is turning around. So to what extent is this fluid flowing along that boundary? It's just kind of not really. It's doing a totally different thing, right? So there is a failure of this fluid to flow along the boundary. And again, unavoidably geometrically linked the curl fails to point along the same direction as the normal vector. And again, these are linked together. If you disengage the boundary from the fluid by turning that little piece of surface, you're also disengaging the normal vector from the curl. Okay. All right, so that's the geometric intuition behind the role of the normal vector and why that normal vector matters to computing circulation. How do y'all feel about that? Yeah.
If you have a surface that's like rippled and has like normals in different directions, how would you do something for that? Would you just calculate out one of the normals?
So what we're doing is the presumption here is that we're looking at a sufficiently small little piece of surface. And keep in mind, when you're doing a surface integral, the definition of a surface integral, you got to chop it up into teeny tiny little pieces. And what we mean by teeny tiny is sufficiently small that the scenario you described isn't really a problem. Yeah, right. Does that make sense?
Yeah.
All right. Good. Okay, so here's some physical manifestations of this. Now, I'm going to start with old news. We've already talked about this here. This was an interpretation of Green's theorem. Recall that if we have a vector field representing the flow of a fluid, by way of velocity here, just to keep it convenient. Of course, I'm imagining this as being water. Water has the constant density anyway, so it doesn't really matter if the density is or is not included. So we have a vector field representing a fluid flow, and we've talked about how, it kind of unavoidably just blunt. The whole purpose of the vector field is to represent the velocity of the fluid, and the leaf is going to do exactly what the fluid is doing. The fluid is flowing with a given velocity, so is the leaf, right? Leafs don't swim upstream, right? Or downstream. So what do we figure though about this leaf's rotation? And again, this leaf is being kind of pushed, if you will, harder on that side and not as hard on that side. And you would sort of expect that then this leaf would start to rotate, and that rotation of the leaf is given by Green's operator. Right? So if you compute Green's operator of a vector field, that's going to tell you, and even though these flow lines are all straight lines, it's not about whether the flow lines themselves go in circles, per the sort of easiest example kind of picture that we wrote down here. Green's operator, aka circulation density, is telling you, independent of the flow lines, yeah, but what's a little leaf going to do? Is there really a kind of a twisting aspect in any sense of this fluid flow? And Green's operator is that thing that measures that. Very cool, very powerful. So here's the analogous thing in 3 dimensions. In 3 dimensions, again, we've got a fluid. This time I'm thinking of the fluid as being air. I don't know, I find this more sort of satisfying. I don't like to visualize myself being surrounded by water. It's, creepy, right? So I'm imagining this as being air, and imagine that the air is flowing around. Now here I have the air flowing around in a, literal, circular flow lines, just to keep the picture as relatable as possible. When you have that, the curl, wrong color. The curl tells you how little floating balloons being moved around by the air, how are they going to be rotating, right? So the curl, again, is going to be pointing that way per the rotation of the fluid. What's the balloon going to do? It's going to move in whatever way the air that's supporting it tells it to move. And if there is a net overall rotational aspect of the fluid, then that balloon is going to be also rotating in the same way. This is assuming a perfectly balanced, floating, perfectly symmetric, spherical balloon with enough sort of cohesion, adhesion between the air and the rubber of the balloon to make it actually kind of get pushed by the air. Okay, how we doing? Everybody all right? Okay. Notice curl tells us two things. It gives the axis that we're rotating around, and it gives us, in some sense, a numerical measurement of how much of a rotation there is. Now, what is the actual angular speed of the rotation of the balloon? Oh, well, that depends on a lot of things. It depends on the moment of inertia of the balloon and the friction coefficient between the air and the rubber and a bunch of other stuff. It's not our problem, right? But just in terms of more versus less, the magnitude of the curl tells you, in some sense, how much. Okay, is everybody all right? Alrighty. A very quick discussion of magnetic fields. This is not a physics course. We don't have time to do a bunch of physics stuff that we just can't squeeze in. But I wanted to show you just a little bit about current and magnetic fields and their relationship, partly because I want to be able to relate this to physics courses you may have already taken, partly because I want to relate this to physics courses you may take in the future, right? But also because it is a wonderful physical manifestation of exactly what we're talking about. So this is empirically reality. I don't know why. Nobody knows why magnetic fields are what they are. We just noticed that, oh my gosh, look, this is what they do. How about that? It's just purely observation that this is how the universe works. Why? Who knows? But the reality is that if you have a current flow field, so this is a flow of charged particles, right? Now, very often the flow of charged particles is confined to a wire, right? And all the little charged particles are moving along in the wire. Okay. I mean, that is a very common scenario, the way we have, electronics set up and stuff these days. But more generally, we could imagine charged particles flowing in space. The wire special case is just a special case of that more generalized idea. Anyway, when you have a flow of particles, I'm going to call this a current flow field, or sometimes a current field. And the observed physical reality is that this creates something called a magnetic field, which kind of rotates around the current. And this is a physics thing, but the which way does it go turns out in I'm going to say kind of a satisfying coincidence, the right hand, human right hand. Not that it has to, not because right hands are in any way sort of naturally better, but this is just the way it happened to work out, again, empirically. If the current's in the direction of the thumb, then the magnetic field's in the direction, rotating around in the direction that your fingers rotate. Okay. So, all right, with that observed, if you ask what is a flux of the flow field, if you think about it, the flux of a flow field, well, the whole purpose of flux, our motivating example of flux, was that it measures how much of that fluid is passing through a given surface. Well, we have a name for how much of the fluid of charged particles is flowing through a given surface. That's current. Is how many charged particles per unit time passing through a given fixed surface. And again, if you haven't had the physics before, don't worry about it. But so having written that down, notice I can, for free, multiply on both sides by any constant I feel like. I'm going to multiply by this one because empirically also we observe this. And again, it's just empirical. But the more current there is, the more magnetic circulation there is in loops going around that current. Again, purely empirical. Don't ask me why that is. Whoever created this universe we live in, ask them. It's not. Nobody knows. This is just what it is. Right? Okay. So again, we find ourselves in this kind of algebraically familiar situation. We write down Stokes' theorem, and all of a sudden, this observation about the relationship between current and magnetic circulation connects up to a seemingly different statement about the flow field and the curl of the magnetic field. So again, these are morally equivalent as statements. These are connected by way of Stokes's theorem, and so as such, these are considered to be the same equation, just different versions of the same equation. So the one on the left is called the integral form because it represents integrals, as you see how it's written, and the version on the right is called the differential form because it's in terms of a derivative. Okay. All right, so again, that's a little physics digression, but I think it's a nice example. And when you get into an E&M class, if you haven't already, I hope that this will be a useful point of view. Yep.
Well, what's mu zero?
It's a observed empirical physical constant. Oh. Yeah, and ask a physicist for more about that. But ultimately, it's just empirical. Yeah. Yep.
What was I again?
What's what now?
What was I?
Oh, I is current. Yeah. Right, so number of charged particles per unit time passing through a fixed surface. Right. Okay. All right. So, y'all may recall this discussion here. This is a copy, straight up, Control-C, Control-V, literally, copy of the discussion we had back in Chapter 6, where we talked about a local test, right? Namely, if you have a vector field, and you'd like to know if that vector field is or is not a gradient. How do we decide if it is or is not a gradient? The answer ended up being just look and see what the Green's operator does. Is Green's operator 0? Then yes, it is a gradient. Is Green's operator not 0? Then no, it's not a gradient. Right? It's this wonderfully convenient little local test. You do a computation, you look at your result, you see if you get 0, that answers your whole question about gradient. Now, how did we do that? Well, we had certain observations about the vector field, gradients being related to path independence, different way to say path independence. And we connected them to these statements about Green's operator by way of just noticing that all closed line integrals are double integrals of Green's operator. So Green's operator was the thing that connected the green statements to the blue statements. And thus, Green's theorem is the thing that gives us this local test. Right? And then I made a statement, kind of a vague statement that, yeah, you can do something kind of like this in 3 dimensions as well, but it requires a different theorem. Well, here we are. In 3 dimensions, again, old news, we already know that being a gradient, being path independent, having this other version of how to say path independence, these are all simultaneous. Again, assuming everything is, we have to assume regularity. I'm going to keep throwing these disclaimers in there periodically. If there's singularities or discontinuities, all bets are off. Everything's changed. So there's some weird counterexamples to worry about. But assuming everything is nice, all these properties I have in green are equivalent. Again, that's old news. I'm going to observe analogously that if you have a flux that's 0 through every surface, no matter what surface you're looking at, well then that integrand has to be 0. Same observation as we made, morally equivalent observation as we made in 2 dimensions. And the connection between these 2 statements is our new theorem. The thing that was missing when we stated but did not prove this back in chapter 6. The connection between closed line integrals and flux integrals of the curl operator. We now have Stokes' theorem. Here it is. And so again, connection made, and again, that's why this local test worked. We, again, stated this back in Chapter 6, but I didn't give you any real legitimate argument for it, because, again, I didn't have Stokes' theorem. My hands were tied. I didn't have what I needed. Now that I have that, you see, we have an understanding of why curl, being 0 or not 0, tells whether your vector field is a gradient or not a gradient. How we doing? Everybody happy? There's a lot to digest there. There's a tremendous amount of ideas on the page there. Give yourself the time necessary to swallow that comfortably. Okay. All right. Okay, here's a new idea. Well, again, I'm going to introduce this new idea by analogy. I like analogies between different dimensions because you can use your intuition in the one existing context to help you make sense out of the new context. So let me remind you, before we dimension it up, let me remind you what path independence means. Path independence means that if you have any scenario where one curve and another curve have the same boundary points. That means they start at the same point, they end at the same point. And that, of course, is very important to the property that we're describing here. It's only in reference to when you have two curves that share the same starting point, same ending point. In that scenario, sometimes it's the case that no matter what curves you pick, no matter what C1 and C2 are, the two line integrals will just always be the same. This is what we mean by path independence. Path independence means that the line integrals are always the same as long as the curves start and end at the same point. So again, review. This is an old idea, right? Equivalent version of that is that all the closed line integrals are equal to 0. Different way to say the same thing. All right. So here's a extremely powerful and I think underappreciated fact. Lots of multivariable textbooks do not include the following generalization, sort of extension, I'll call it, of path independence, and it's a big gap. This is a really important extension, and that is one dimension up. We're going to talk about now something called surface independence. It's extremely analogous. Just add one to the dimension of everything. Path independence becomes surface independence. Here we go. Suppose I have a surface and another surface that have the same boundary. Now let's think that through for a second. When I say two surfaces have the same boundary, the boundary of a surface is a curve. It's not points. There's not a boundary of starting point and ending point. The boundary does not consist of a mere 2 points. The boundary is an entire curve. So, two surfaces with the same boundary curve, you can imagine maybe my left hand is one surface, my right hand is one surface. Having the same boundary curve means that it's like you're holding a bug inside of your hands, right? They have to meet up all the way around. That means you're enclosing a volume. That makes sense? Okay, so what would be the analogous concept to path independence here? And no comment, by the way, yet on whether or not the property that I'm about to describe is ever achieved. But just what would be the analogous property? The analogous property would be that somehow, in any such scenario, when I have two such surfaces, somehow that the flux through the one surface and the flux through the other surface would have to be the same. This is what we would call surface independent, right? And in the same way that the very first time you look at path independence, it's like, wait a minute, all curves? All curves. You gotta be kidding me. There's so many curves that start and end at the same point. They all have to give me the same value of the line integral? Get out of town. Come on, there's no way. How could this possibly be, right? It seems highly implausible. Likewise here, all surfaces that have that same boundary curve would all have to give you the same flux. Come on. How could this be? Right? It's going to turn out that there are not only some vector fields that are surface independent, it turns out that there's a lot of them. There's an entire category of them. We'll get to that in just a minute. Let me rephrase this a little bit, though, and I want to pay careful attention before I do to I said the word boundary, right? I need both of these surfaces to have the same boundary. Oops, stylus. Got to have the same boundary. Remember, boundary is an oriented thing. So when I say that these two curves have to have, these two surfaces have to have the same boundary curve, that's saying that their normal vectors have to relate correspondingly in some sense. So as I have it drawn here, what I would need is for the green surface to be oriented, which you're going to be tempted to call inward, and I would need the blue surface to be oriented, what you're going to be tempted to call outward, and this is going to seem uncomfortable. Wait a minute, why is one inward and one outward? That doesn't seem the same, that seems opposite. But if you play the game with your thumb, right? Thumb in the direction of the normal, look at the swirl, see how it sideswipes against the boundary curve, and this is a nice exercise, everybody should do it. What you're going to find is that these are the orientations that give this purple orientation that I've indicated on the shared boundary curve. One has to be inward, one has to be outward. Seems incompatible. Now, let me point out, not news. Check it out in this situation. C1 and C2 have the same starting point, same ending point. But wait a minute, one of them's going counterclockwise. One of them's going clockwise. Aren't they kind of opposite? See what I'm saying? So what we need to do is distinguish between what we mean when we say two curves have same or opposite orientations. Really, the first thing we need to recognize is that there's actually no way to compare orientations on different curves. They're different curves. For any given single curve, yes, there are two choices. And we describe those two choices by what are the tangent vectors at a single point, and there's your two options. These are different curves. Their orientation vectors are at different points. There is no same. There is no opposite. Right? So what we can talk about, and it's reasonable, I suppose, is how they give an orientation to their shared boundary. In other words, what is their boundary? We can talk about how they may or may not relate in terms of what they are a boundary of. These are different points of view, right? So, yeah, you could say one of these is clockwise and one of these is counterclockwise, but that's really not the point. The point is they have the same starting point. They have the same ending point. So likewise down here, right? The point, how these are part of the boundary of the solid that they enclose is not what we require. Inward, outward to the solid is irrelevant. I'm not interested in the solid yet. Right? What we're interested in is what is the boundary that they induce on their shared boundary curve. What is the orientation that they induce on the shared boundary curve? So here's by the way, just one more way to say it. Instead of thinking of these as one's inward and one's outward, how about this? They're both upward. Right? That makes them seem more same-ish and less opposite-ish. Okay, anyway, enough about boundaries. With all of that noted, observe that these two fluxes being the same is the same statement as saying that the sum of them, namely that what ends up being this closed surface integral, would have to be 0. Because two things being equal is the same as saying that their difference is 0. Okay, so all together now I want to zoom out and get these both on the same page at the same time. Notice the tremendously strong analogies between this property called path independence that I described a week or two ago and this new thing called surface independence. Again, I've laid it out on the page deliberately to try to be as analogous as possible to underscore the analogy as much as possible. Surface independence is just the same as path independence one dimension up. Okay. All right. So, does this ever happen, or is this a completely abstract conversation? Yeah, it turns out it happens all the time, and it happens for analogous reasons. So, for example, let's imagine that we have a curl. Come on. Sorry. Elbow. Let's imagine we have a curl. And I'm entertaining these flux integrals, through one surface versus another surface. Are these two flux integrals equal? Well, here's the thing. If it's a curl, then each of them is computed by way of Stokes' theorem as a line integral on their shared boundary. Right? The blue integral is computed as a line integral on its boundary. The green integral is computed as a line integral on its boundary. They have the same boundary. Therefore, these two flux integrals are computed by the exact same line integral. So they are equal to each other. And therefore, this is a surface-independent vector field. Now, another, I think, really healthy exercise is to look back at the analogous argument that we made back in Chapter 6, observing that all gradients are path-independent. Here, we're using a, context different, of course, but analogous argument to show that all curls are surface-independent. Okay. All right. So, another local test. We've talked through just now how being a curl means surface independent. I claim, by the way, vice versa. Again, that's much harder to prove. It's beyond the context of this class. I don't want to prove it both ways. But being a curl, being surface independent, restating surface independence as all closed fluxes equals zero. These are all simultaneous. Again, appropriate, we need to make sure everything is continuously differentiable. Big problems come up if there's regularity issues. Not our problem in this course. So this is what surface independence looks like. Here's some statements that I can make about divergence. If all triple integrals of divergence are zero, well then surely the divergence itself must be zero. How can an integral of something always be zero no matter what the domain is unless the thing itself is identically zero? Right? What's the connection between these? Well, you can almost guess from the page. I would need for there to be a relationship between boundary fluxes and triple integrals of divergence. Conveniently, we have just such a theorem. The theorem relating triple integrals of divergence with closed boundary fluxes is the divergence theorem, Gauss's divergence theorem. So again, the morally equivalent argument. Boom, right? Same ideas. Give us this connection on how to test, our local test, that is, for whether something is surface independent. If you want to know if something's surface independent, compute the divergence, see if you get zero. If you do, cool, you're in business. Does that make sense? If you don't, then, by the way, no, it's not surface independent. You're not in business. You can't cite surface independence. Let's see this in action. Here is an example. This, by the way, would be a pretty hard, this would be a pretty inconvenient problem if it wasn't for surface independence. Let's think about how I would compute the flux of this vector field through this surface S that is described in a certain way. It's part of a certain graph. The part above the XY plane, oriented downward, by the way, that just to kind of throw a curveball into the mix. How would I compute this flux? It's not a boundary of anything, right? If you look at this surface itself, and by the way, let me draw this surface. Here we go. The part. Let's see. Yeah, okay. First, let me do this first. The part of the paraboloid that's above the XY plane is this thing right here. It is not a boundary. Now, there's a temptation to say, sure it is. There's a temptation to say, well, isn't it the boundary of this solid? No, it is not. This is a very important, lots of students mess this up, by the way. This is a very subtle but important distinction. The surface S is described unambiguously as part of the paraboloid. This thing down here is not part of the paraboloid. That blue surface at the bottom, not part of the paraboloid. It just isn't. Right? This whole thing over here, this is just a clarification of which part we're talking about. This does not say S is the part of the paraboloid with z greater than equal to 0 combined with the part of z equals 0 inside of the paraboloid. That whole second clause is not in there. Right? Does everybody see this distinction? It's very important to realize S is just the described part of the paraboloid. It's like an upside down bowl. It is open. The cereal falls out. Right? Not closed. This is not a Tupperware. This is an open cereal bowl. Is everybody comfortable with that? I want to make sure everybody's clear on the distinction. Big common problem that students mistake that students will make in on exams. Okay. All right. Okay, so all of that clarified. I've got a surface. I've got a vector field. I want to compute a flux. I guess I could parameterize. I mean, it's a graph. I could do the graph parameterization, but I don't know. It seems like that's going to have a lot of computations in it, and frankly, it would be uglier than it looks. So that said, how do we deal with this? Well, my vector field. I can compute the divergence of that vector field effortlessly at a glance. I don't hardly even need to write down the algebra. I can just look and see there's no x's in the first component. There's no y's in the second component. There's no z's in the third component. This divergence is not only 0, it's the sum of 3 zeros. It's an easy 0. Right? So the divergence is 0. That tells me that my vector field is surface independent, and now we have a powerful tool at our disposal. I can take any other surface that I choose, up to me, right? Free choice to me to pick any other surface I like that has the same boundary curve. It's got to have the same boundary curve. Any surface that I like, and just change the surface. Well, this is too good to be true, right? But it is. And I'm going to go ahead and pick, let's see, we've got to be careful. First of all, let's be careful about the boundary. The boundary is this curve right here. What's my favorite surface that has this circle down here, or no, I guess that's an ellipse, this curve down here in the XY plane as its boundary. And everybody's going to have different personal preferences. I like whatever's the easiest. I'm going to pick that blue flat surface right there. Everybody see my motivation? Okay. So, cool. Phooey on the original surface. I don't like it. All I needed now that I realize that I have surface independence, right? I can pick any surface I want. I don't like the original one. I'm going to pick this nice flat blue one. And then the problem just becomes a lot easier. My normal vector is easy to write down. There it is. It's just 0, 0, -1. Do be careful about the orientations. You got to think through how the downward orientation on the original surface gives you this orientation on the boundary curve, which is compatible only with this orientation, the downward orientation on the shared surface. You got to connect those dots. It is not fair to say, "Oh, downward, therefore downward." That's not what was. That's two significant logical leaps that do not follow. right? You can't just say, oh, well, the first one was downward, so the second one's has to be downward also. You have to infer the correct orientation on the boundary, and then from that infer the correct orientation on the second surface. I hope that's clear. Is everybody happy with that? Okay. So with that done, we have an easy normal vector. You gotta love it when you have easy unit normal vectors. This, right, dotted with that is an easy dot product. It gives me just minus xy. And I have a relatively easy integral. Turns it at a glance, it's zero by symmetry, right? Of course, think through the details of that symmetry argument, but much easier. Calculation, didn't have to get my hands dirty, didn't have to do a bunch of, big polynomials. I didn't have to integrate the big polynomials over a solid ellipse, which would have been inconvenient, right? So, life is good. How we doing? Is everybody happy? Okay. Yes?
So if I don't do the symmetry argument, I'd have to parameterize the surface?
Yeah, that's right. You'd have to parameterize this. Let's see here. You would have to parameterize our newly chosen surface there, it would. That's another way to go. But again, you would have to you'd be doing an integral on an ellipse, which is, golly, how would you do that integral on that ellipse? What I would probably do is, it would be hard. Yeah. Okay. Okie dokie. All right. So, let me remind y'all in the 2.5 minutes I have left, we have the strategic diagram for R2. I want to point out that in the same ways that this kind of organizes and does bookkeeping for you for vector calculus theorems in 2 dimensions, we have an analogous thing in 3 dimensions. And by the way, for all the same reasons, we have this, what I'm calling a diagram, because this is what you get when you take some very sophisticated constructions, cochain complexes of differential forms and all this more nasty stuff that we can't talk about in 219. If you take all that, boil down all of the sophistication and the rigor and the precision, etc., and just what's kind of going on, relatably speaking, in how we're going to be doing stuff in 3 dimensions. This is what you get, right? So let me point out all of the different patterns here. If you want to know if something is or is not a gradient, take the curl and see if you do or don't get 0. That's an old fact that we did revisit today, by the way, but then check this out. If you want to know whether a vector field is or is not a curl, take the divergence. See if you do or don't get 0. That's a brand new fact from today. So that's this is a real eyebrow raiser, right? The fact that the way the objects, the way these operators relate to each other are diagrammatically identical, right? That's useful information, right? This is strategic streamlining. You don't have to remember separate facts about, which operator does what purpose. No, just remember the pattern on the diagram. The diagram does the bookkeeping for you. Okay. Similarly, let's see here. Remember we talked about the fundamental theorem of line integrals. If you have a function, you take its gradient. If you have a curve and you look at the boundary points, then this evaluation and this evaluation are the same. I made this observation back in 2 dimensions. Here it is in 3 dimensions. Really the same observation. But now, and I don't know if this is going to lay out on the page as well, but let's see. Same thing for Gauss's divergence theorem. It's the same theorem. Diagrammatically, it's exact same pattern for Gauss's divergence theorem. And we see now also the exact same pattern for Stokes's curl theorem. Diagrammatically, the same. So now you can think of those 3 theorems as being 3 separate theorems. Yeah, okay, sure, yes you could. But instead, think of it as one pattern that replicates 3 times on this diagram. It's really the same pattern, and arguably, by the way, I will point out, it replicates 5 different times because it's the same pattern as for Green's theorem and the 2D line integral theorem as well. So understanding the patterns represented by the diagrams, you're in business and you don't have to think of these as all separate theorems. It's just the same thing over and over again. Okay, and we're surely out of time by now, so we will, there's a little bit more I'm going to say about this next time, and then most of what I'm going to do tomorrow, Friday, is go through a bunch of examples of how to use the diagrams, how to compute line integrals, how to use all the tools that we've been developing. So make sure to come on Friday. It's going to be a really rubber meets the road useful day. See y'all later.